almost ready for the last morning session before lunch. And I'm Bo-Yin Yang of Academia Sinica. And we have up here Guillaume Muro, who will teach us about a reduction of Hawk to a new problem. Like another minute.
Should we go? Right, okay. Thanks, Bo-Yin, for the introduction, and good morning, everyone. So this is a joint work with Clément Chevignard, Thomas Espito, Alice Pellemari, Yuri Plachuk, and Alexandre Wallet. And so my goal in this talk is to prove a polynomial time reduction from the module lattice isomorphism problem on the specific case of Hawk module lattice to some problem on ideals in quaternion algebras. So let's start with a bit of context. In 2022, Ducap, Osselwaite, Poules, and Van Norden, they introduced a new lattice problem called the module lattice isomorphism problem, module LIP for short. And they used it to design a signature scheme, Hawk. So Hawk is a nice candidate for the additional call for signature schemes. It's based on module LIP over cyclotomic fields. It's efficient and compact. In 2023, with Alice Pellemari, Yuri Plachuk, and Alexandre Wallet, we gave a heuristic polynomial time algorithm for solving module LIP for rank 2 modules over totally real fields. But this work doesn't break Hawk because Hawk uses cyclotomic fields, and cyclotomic fields are not totally real normal fields. So in this talk, we focus on this case, the case of cyclotomic fields, or more generally, the case of CM fields. And so we proved the polynomial time reduction for rank 2 module LIP, as in Hawk, to some problem on ideals in a quaternion algebra. So morally, the idea is to go from a problem on rank 2 modules over field K to a problem on rank 1 modules, ideals, in some quadratic extension of the field. So in this case, a quaternion algebra. Okay, so let me give the definition of the problem. First, I will begin with the lattice isomorphism problem, in which you are given two lattices, L and L prime. You know that they are isomorphic. That means that L prime is the image of L by some orthogonal map. So here's an example in dimension 2. So on the left-hand side is L with basis B, and on the right-hand side, some rotation of L, L prime, with basis C. And if you look at the right-hand side, so there are two bases of L prime, C, and the image of B by the rotation. There are two bases of the same lattice, so there exists a relation of the form C equals theta BU, where theta is unknown, and U is some unimodular matrix. And the lattice isomorphism problem is exactly to compute either theta or U, given B and C. So this problem has been studied for quite a long time, and all the algorithms for solving LIP, they need to enumerate short vectors, which is already a hard problem, so we have good reasons to think that LIP is a hard problem too. So why not to use it for crypto? And to make it even more efficient and compact, the authors of Hawk, they used module lattices. So we consider sets of the following form. K is a number field, a finite dimensional extension of the field of rational numbers. Zk is the ring of integers. And we are given n vectors in Kn, which are K linearly independent. And so what we call a module lattice is the set of combinations of these vectors with coefficient in Zk. An important example for us is the case of power 2 cyclotomic fields. So they are given by Q of x modulo this polynomial, x to the 2 to the m plus 1. And so in this case, Zk is Z of x modulo the same polynomial. These fields are equipped with an automorphism called the complex conjugation. So in this talk, I will only focus on power to cyclotomic fields because they are used in Hawk. But this work generalizes to, this works for any CM field. Okay, so we have everything to define the module leap. So module leap is basically the restriction of leap to module lattices, but you also want theta and u to preserve the algebraic structure you added. So that means you're looking for a theta with coefficient in k, and u has coefficient in zk. An example, so this is the module lattice used in Hawk. So basically 2 orthogonal copies of zk, the ring of integers. And the basis B is simply the identity matrix. So an input of module leap is the basis C of a module lattice L, which is k isomorphic to H. The security of Hawk is related to the hardness of this problem in the sense that if you are able to break module leap on H, you get a key recovery. So in the following, to keep it simple, we will only do it for the Hawk module lattice. Okay, so let me explain how the reduction works. So the framework is the following. K is the power of 2 cyclotomic fields, B is the 2x2 identity matrix, and C is some theta BU. B and C, they are public, and theta and U are secret. And the idea is basically to get information on U from the gram matrix H associated to C. So H is equal to C star C, where C star is the transpose and conjugate of C. If you write down this matrix, so H is in fact equals to U star U. If you expand the product, you get this Hermitian matrix. And look at the diagonal coefficients. They are invariant under complex conjugation. So in fact, there are elements of a subfield of K, which is called the totally real subfield of K. If you're a bit lost, you may think of K is Q of I, and then I'm just saying that the diagonal coefficient, they are rational numbers. So in fact, for power to cyclotomic fields, we have K equals F plus Fi, where F is the totally real subfield. So if we write down X equals X1 plus I X2, and same thing for Y, then we see that the first coefficient of H is the sum of 4 squares in ZF. And seeing sum of 4 squares, you may think of quaternions. So we introduce this quaternion algebra A. So this has dimension 4 over F with basis 1, Ij, and Ij, and with the usual rules. So I squared is equal to J squared equal negative 1, and Ji is equal to negative Ij. So this is, because of the last rule, this is a non-commutative algebra. It contains K as a commutative subfield, and it also has a complex conjugation map which extends the one on K. What we call the reduced norm of a quaternion alpha is the product alpha times alpha bar. So we recover this way our sum of 4 squares. The idea is to see the first column xy of the secret matrix U we aim at recovering as a quaternion. So this corresponds to the quaternion alpha equals x plus yj. And its reduced norm is precisely the first coefficient of the gram matrix, the sum of 4 squares. So if we are able to compute all the solutions in zk plus zkj to this equation, reduced norm of alpha is equals to q, the first coefficient of h, then among the solutions we know that they are the first column of u, and we do it for the last coefficient of h, so we can recover the second column of u the same way. So just a remark, in the introduction I tell you about a previous work where we solved module leap over totally real fields, and we needed to solve this kind of equation, but we seeked for solutions alpha in zk and not quaternions. And in this case, you can ensure that there are not too many solutions and you can compute them efficiently. But in the case where you are looking for solution alpha, which are quaternions, you can prove that there are too many solutions to hope to enumerate them all. And also, we don't know how to compute quaternions satisfying this equation. Okay, so the idea was to get some more information coming from H to reduce the solution space. Let me denote H, the gram matrix, this way, and U, the secret unimodular matrix, this way. I set alpha, the quaternion corresponding to the first column of U, and beta corresponding to the second column. Then we proved the following lemma, which is a characterization of whether U is a solution. So that means whether U star U is equal to H. And this is the case if and only if. So the reduced norm of alpha is equal to Q1, the first coefficient of the gram matrix, something we saw before. But also a condition on alpha times beta inverse. The proof is a direct computation. And if you look at the second equation on the right-hand side, you see that alpha beta inverse is given by something which is completely determined by the public gram matrix. Okay? And also a conclusion is that we only need to recover alpha because we get a beta which is determined by the alpha uniquely. So now the question is, can we retrieve alpha from alpha beta inverse? Let's forget about quaternion just for a moment. Suppose that we are given integers and a and b, they are co-prime. So suppose that we know the fraction a over b. How can we get a? Well, you can consider the fractional ideal a over b times z. So you take the integer multiples of a over b, you intersect with the integers, and then you get the ideal generated by a. You take a generator, and so you get a up to the sign. Well, actually, the same works with quaternions, but you replace z by O, which is zk plus zkj, which is an order in the quaternion algebra. And we prove the following. So the following ideal, alpha beta inverse over O intersected with O, is in fact equal to the principal ideal generated by alpha. And so morally, the GCD of alpha and beta is 1 here because they correspond to vectors which generate the whole lattice zk squared. Okay, so to sum up, the idea was to see the columns of the secret matrix U as quaternions, alpha and beta. From the public gram matrix H, we're able to compute alpha beta inverse. And from alpha beta inverse, we can build the principal ideal generated by alpha. So now we have reduced to the following problem, which we call the reduced norm principal ideal problem. So given as input a quaternionic ideal I and some element Q in F, the problem is to recover, if there exists one, a generator of I with reduced norm equals to Q. Okay, so this way we obtain a polynomial time reduction from moduli on Hawk lattice H to this problem in O. And more generally, it can be adapted to any rank 2 module in K2. What about the problem we reduced to? So actually, the state of the art is due to Kirchner and Voigt. And so basically, you can solve the problem by computing a shortest vector in the ideal, which can be seen as a rank 2 times the dimension of K lattice. Something important I like to notice is that when I is in fact not a quaternion ideal, but a commutative ideal, an ideal in K, and you are given Q in F, there exists a polynomial time algorithm due to Gentry and Sidlow and generalized by Lenstra and Silverberg. So an algorithm to compute a generator G of I with reduced norm equals to Q. Okay, so an open question is to see if there exists some adaptation of this Gentry and Sidlow algorithm for quaternions. This is an open question. So to conclude, we proved a connection between a lattice problem, between moduli for rank 2 modules to the world of quaternions. To our knowledge, this is the first time. Quaternions are something isogenists are more used to. So this might be a new angle of attack on Hawk. And so the big open question is to understand better the cryptanalysis of the reduced norm problem, the reduced norm principal ideal problem. Okay, so thank you.
We have plenty of time for questions. And so, I mean, I have a question which is, we know something about this NRD-PIP problem, like how it relates, I mean, as you said above, and how the state art is. Yeah. And so those people have conjectures about how hard this would probably be like in the space of the usual lattice problems.
So you're talking about the complexity of NRD-PIP or
yeah.
Hawk? Yeah.
Yeah.
So NRD-PIP, actually, we introduced the problem, so it's new. Kirschner and Voigt, they only give algorithms to compute generators of quaternionic ideals with no restriction on the reduced norm. And our hope is to see if there exists an important speedup, like Gentry-Silva algorithm, in this case for quaternions, for non-commutative ideals.
I see.
Hello, thank you for your talk. An definite quaternion algebra can be seen as the image as left regular representation of an arithmetic Fuchsian group of type 1. Then, so do you think that so you are looking for solutions of the normic equation, so a representation of Q in terms of as a reduced norm of a quaternion? Do you think that can you exploit any techniques regarding directly to the Fuchsian group? For instance, a reduction algorithm like bringing things to the fundamental domain to retrieve a representation. So can this be useful?
So thank you for the questions. Actually, I'm not really used to this kind of algorithmic on quaternions. So I don't know if there is something to do, but I'd be happy to discuss this. Yeah.
Hi, thank you for the talk. I just wanted to ask for a clarification. So in your last year's paper, your work was heuristic. Can you just say if this was also heuristic or it's like...
Okay, so in last year's talk, we enumerated all the solutions to the norm equations. We didn't use the trick. Yeah, so we didn't use this trick to reduce the solution of the solution space. So we were interested in finding all the solutions, and to ensure that there are not too many, we introduced randomization of H. So basically, if the first coefficient generates an ideal with too many prime factors, we just we randomize this matrix until it generates a prime ideal. And in this case, you are sure that there are not too many solutions. So we needed a heuristic to, in this case. But actually, this trick proves that there exists, so over totally real fields, this removes the heuristic part. Yeah.
Any other questions?
So regarding the algorithm by Kirschner, so it's an instance of PIP over quaternions. So we know that pip over number fields is kind of sub-exponential, at least. So is it quantum sub-exponential, maybe?
Yeah.
So is it the case for the quaternion version, or what's the complexity? If we ignore the additional condition on the norm.
Yeah, so actually they solved it without the condition on the norm. And so basically you need to compute a short vector which corresponds to a generator, and if you want to transform this solution to have the reduced norm exactly you want to, you also need the units so we have a polynomial time quantum pre-computation in this case. Yeah.
Okay, let's thank Gurem again.
Thanks.
And next up is Wessel van Verden, and now talking about the cryptanalytic result on the modular lip, and its floor is yours.
Okay, thank you for the introduction, and thank you all for being here. So I hope you all paid attention to the previous talk, because in this talk we will continue the story and look at the cryptanalysis of rank 2 modular lip. So in the previous talk we have seen, that was already mentioned there, that in last year's Eurocrypt there was an attack on the rank 2 modular lip case when your number field was totally real. And in this case, they could fully solve it. And in the previous talk, we have seen that if we look at the same problem over CM fields, then we can only reduce it to a variant of a principal ideal problem over quaternion algebras, and there we cannot really, at least it doesn't seem obvious how to solve it efficiently. So we have these two cases, and then the natural question is, what can we say about all the other number fields that are not totally real or are not a CM field? So let's first give some background on what these number fields are. So for a number field, we can just consider like rational polynomials quotiented out by some monic irreducible polynomial of certain degree d. And one nice example that we consider in this talk is the n-true prime field, where we quotient out by this x to the d minus x minus 1. And this will be one of these examples of a number field that's not totally real and also not the CM field. And the ring of integers, in the previous talk, this was denoted by z of k. Here we use the O of k. You can just assume that's essentially like integer polynomials in this thing. And then we will only consider now the rank 2 modular lip problem in like the simplest case, where we just take look at OK squared. And that's like the same simple case that we considered in the previous talk. In the full paper, we consider like any rank 2 letters. And we have seen that one way to define this problem in the previous talk is that given some basis b of of OK squared, we can look at this Gram matrix, b star b, and the problem is to, given this Gram matrix, recover this basis b. However, this conjugation, like this b star, this conjugate transpose, isn't always properly defined in K. So if you have a totally real number field, this conjugation doesn't do anything, so it's just identity. And if you have a CM field, you have a very natural way to do a conjugation, so that's also fine. But in general, you don't have this. So already this definition of the problem is kind of not correct. So let's have a look at like what's the correct definition. And also, this essentially is the cause of most of the technical problems that we have in our work. And most of the technical problems I won't get into detail within this talk, but that was most of like the work that was in this paper. Okay, so we will have a look at embeddings of our number field. So given this polynomial that defines our number field, we can look at its complex roots. So we have d roots alpha 1 and 2 alpha d. And for each of them, we can define a field embedding, where we send any of these polynomials in our number field, we send the monomial x to one of these roots. And if you do this, then essentially addition and multiplication in your number field corresponds precisely to addition and multiplication in the complex numbers. And if we take all these D roots, so we have like D of these embeddings, if we just concatenate them, we get an embedding of our number field into C to the D. So some of these embeddings we find quite special because they correspond to like the real roots of a polynomial, and they don't really embed into C, but essentially just into the real numbers, and we call these real embeddings. And all the others we just call complex embeddings. One thing to note is that complex embeddings always occur in pairs because if alpha is the root of a polynomial, then the conjugate is also a root of the same polynomial. And now when we have this embedding and we are in C to the D, we have a very natural way to conjugate there. So what we can try to do is kind of lift this conjugation that we have in the complex numbers or in C to the D back to our number field. So we take an element in our number field, y, we map it to this to C to the D, we conjugate there, and then we try to invert this embedding. And this is actually not always possible. However, you can do it if you kind of tensor your number field with the real numbers, and you extend your embedding to that. But that's like one of these already technical details that I don't want to get into further. But now we have some sense of conjugation, and in principle now this B star B makes sense. Equivalently, we can also just say we really only look at this conjugation in this embedding. So what we get is kind of a new gram matrix where we just look at the embedding of our matrix B, where we just apply it to each of the coefficients, and we look at conjugate transpose of that times itself. And given this, we want to recover this basis B. Okay, so now that we have a proper statement of what the problem is, let's have a quick look at what the current state of the art is in the cryptanalysis. So on one side, we have this totally real case. And in terms of these embeddings, that means that all these embeddings are real embeddings. So yeah, you just go into the real numbers. And in that case, it was shown to be broken, the problem. On the other side, we have the case of Hawk and of CM fields, and these are totally complex, and you have only complex embeddings. And in this case, it seems you turned into these quaternion algebras, and things looked a bit more complex. And more specifically, what we saw in this CM field case is that we ended up with these kind of sum of four square norm equations, and that's where these quaternion algebras pop up. And what actually happened in the totally real case is that we just had like a sum of two squares, and these actually they could efficiently recover. So again, the question is what happens in between? Like what happens if we have at least one real embedding, essentially? So some examples here is like any number field of odd degree, like because if that's odd degree and the complex embeddings occur in pairs, you need to have at least one real embedding. So this is a huge class of number fields, of course. And as a special example of a number field that actually occurs in cryptography, so for example, these totally real fields, they were broken, but so far I don't think we really are using totally real fields in cryptography. But this entropy prime field is an example of a non-totally real and non-CM field that is actually actively used in cryptography, namely in the entropy prime scheme. So the question is, are we in this sum of four square case, or are we in this sum of two square case? And in this work, we show that we're actually in this sum of two square case, and we can use that to fully break it. Okay, so let's quickly get back to the case where our number field is totally real. So what's the main thing that the authors used for this? Is that if we look at this B star B, then this conjugation doesn't do anything. So what we actually get is just B transpose B. And just looking at the elements of this matrix, so let's quickly go back, like I will define B, we'll just write it like this, with A, B, C, and D. If we write that out, then we get this A bar A plus B bar B, and that's just going to be equivalent to like exactly the same as A squared plus B squared. So from this Gram matrix, we immediately recover A squared plus B squared, and that's what we will use later, the knowledge of this value. But the above is not the case in general, like because if we're not in the totally real case, this conjugation is non-trivial, and A bar A plus B bar B is not going to be equal to A squared plus B squared. But the main idea of our work is that if we look at a real embedding, so we assume we have like at least one real embedding, then we do have that a squared plus b squared and a bar a plus b bar b map to the same real number. Because for this real embedding, this conjugation doesn't do anything. So we don't obtain the value of a squared plus b squared, but we do obtain the value of its real embedding. And then the question is, of course, can we recover a squared plus b squared from this single real embedding? And it turns out, luckily for our work, that yes, we can do this. Okay, so let's have a look at that problem. So in theory, is this even possible? Well, yes, each of these embeddings is injective. So in principle, we could like find the pre-image that's unique. But it's only if you have like infinite precision, if you really work with like real numbers. So in practice, that is a bit more complex. But still have a look at it. We know that a squared plus b squared lives in this ring of integers. So let's just write down a z basis of this ring of integers. So we can do that with like d elements. And then we know that a squared plus b squared is an integer combination of these elements. But this gives us like d unknowns, like we need to guess these integers xi. But at the same time, we have only one equation given by this real embedding. If you would have all the embeddings, you could easily solve it, the unknowns, the equations, but we have only one equation. However, we can assume that all these xi are small, and you can do that assuming that this basis is LLO reduced. I mean, you don't have to assume it, you can just compute that, and also that our input bar matrix is LLO reduced. And in this case, what we want to find is not just any x, but we want to find somewhat small xi. So we want to find a somewhat small integer combinations of these real embeddings of our basis that give precisely or approximately the real embedding of a squared plus b squared. Here I suddenly move to like approximate things, and that is because we cannot compute these things in infinite precision. Like we need to compute them at some high but still polynomial precision. And it turns out that this is precisely a lattice problem. Let's have a look at some kind of fun example where we assume that we have the real number pi and the real number e, which are going to be the two like embeddings. I mean, this is not a real case, but there's two real numbers, and we know that we get some approximation of an integer combination of the two, and we want to recover these x1 and x2. So we have all the integer combinations, like integer multiples of pi and all the integer multiples of e. And the problem is that if we like to look at all the integer combinations of pi and e, then because these things are not independent over the real numbers, they will lie dense in this line. So any point that we have, so for example, if you have any approximation of this 2 pi minus e, then we can approximate it arbitrarily by any integer combination. Like that's, I mean, not any, but like you can find integer combinations that are arbitrarily close to this. So that's not really helpful. But if we only look at small combination, then we see we get some kind of discrete structure at least. So if we get some approximation of this, good approximation of this 2 pi minus e, then we have some hope that we can find this nearby correct combination. But that doesn't mean we can actually do it efficiently, so let's try to do that now. And the problem was that these pi and e are not independent over the real numbers, which makes them very dense in this one direction. So let's just try to not make them dense. So we're just going to make them independent. We're going to force them to be independent. And we're going to do that just by going from 1 dimension to 2 dimension, and we add like a little 1 to this vector here and the rest zeros. And what we then get is this lattice of all these combinations, essentially of, I mean, these two vectors, but essentially of this pi and e. Like each of these points represent some combination. And the combination that we are interested in to find is this, in our case, is this orange point, given this red point. The problem here is that like this point is not even the closest point to this red point. So at first it's like, okay, what are we doing here? But what we can now do is we can try to like stretch this lattice up sideways. And we can do this by just putting some scalar in front of this, like on the first coefficient. And what we see is that we increase this lambda, then the bad points, kind of the bad combinations that we don't want to find, move away from the red point. But the orange point, like the one that we actually want to find, because it lies on the vertical line below our input point, it doesn't move further away, essentially. Like, it will stay at the same distance. And now the room on my slide is up, so I will have to zoom out a bit, essentially, and we're going to stretch it a bit more. And at some point, this target point is going to be, like the point we want to find, this good combination, is going to be the closest point to our target point. And in fact, if you make this scaling factor large enough, LLL is enough to, like lattice reduction is enough to recover this closest lattice point. And then like some small technicality, I talked about finite precision, so we are actually rounding these values to get integer vectors. And luckily, I didn't have to do all the math for like how much precision do you need, because Alice and Damien Stille already did that before, and you only need to have lambda polynomial in all the relevant values. And if we specifically look at the case of entropy prime, we see in practice that quadratic precision is enough in the degree of the number field. So these are like the three elements of B star B, essentially, that we want to recover in B transpose B. Okay, so now we have recovered B transpose B. We just apply this to, we do this procedure for all of these elements. And in particular, we know A squared plus B squared. And now, essentially, what we want to do is we proceed as in the totally real attack, and with some improvements that were made also in the work of the previous talk, but again, with a lot of extra technical obstacles. Now, first, the easy part. The complex, like the square root of -1, which is just denoted by I, is not in our number field, because we have at least one real embedding. This is not possible. And as a result, we can just add it to our number field. We get an extension called L, and we can, if we look at the element A plus BI, then the norm of it, the relative norm of L over K of this element, is going to be this A squared plus B squared. So this is where we have our norm equation that was also in the previous talk and in the totally real attack. And we have no need to go into quaternions, because I doesn't live in our number field, which was actually the case in the previous talk. Then we can, again, also use this trick from the previous talk to recover the ideal generated by Z, which is like this A plus BI. And what we then would like to do is, well, what they do like in the totally real case is this L is a CM field, and given this ideal and Z bar Z, which is exactly equal to A squared plus B squared in their case, they can use Gentry-Seidlow to recover the element Z. However, for our case, L is not a CM field, so we need to generalize this further. So what we do, we give a generalization of the Gentry-Seidlow algorithm for any number field that's what we call so-called like GS-friendly. And this is a very weak condition. Essentially, we expect that most, like all number fields are GS-friendly, but heuristically, we just assume it's the case for us. But then the difficult part is still that in this generalization, what we need is not like this Z bar Z, but we need the value of the absolute embeddings of our element. And the difficult part is that we don't get these automatically from the values of A squared B squared or A bar A plus B bar B. And we have three approaches to solve this last step, which I won't go into, but you can kind of make your choice which one you want. Just to give one detail, if we have a Galois group of our polynomial that is too transitive, then we can actually recover all these embeddings, and we can use our heuristic Gentry-Seidlow algorithm, where this heuristic, like I said, is quite mild. But we also have a case that's completely proven if we have a quantum algorithm, and if we don't have this to transitivity, we have another heuristic algorithm, quantum algorithm, to fully solve it. Okay, to conclude, the security of this rank 2 module lib problem really depends on the number field, and any real embedding will cause problems. And yeah, all these intermediate cases where you have at least one real embedding are broken. Thank you for listening.
We have time for one question. Okay. So presumably this only is only for the modular leap problem. Like, doesn't really say anything about the use of the n-true prime field for like dilithium or like Kyber-like constructions.
No, I mean, it's not clear how it would. I mean, it might suggest that you could have a look at this real embedding and see if you can use it in some way, but like our approach really, like we make no claims about other problems related to the n-true prime field besides rank 2 modular lib. Yeah.
Okay, well, let's thank Veso. And so we have Xiuhan Lin here to talk about security implications for Falcon with floating point computations. Up to you.
Oh, hello, everyone. The title of our paper is "Do Not Disturb a Sleeping Falcon: Floating Point Error Sensitivity of the Falcon Sampler and Its Consequences." This is joint work with Mediti Pozi, Yang Yu, Shiduo Zhang. I'm Xiuhan Lin from Shandong University. In this work, we mainly focus on security implications in Falcon's use and deployment caused by floating point arithmetic errors. We found that Falcon Gaussian samplers is sensitive to floating point arithmetic errors, and in the case of deterministic variance of Falcon, following some floating point arithmetic catalysis, so one can mount exact signing key recovery. So in our attacks, for some de-randomized settings, one can mount a full key recovery within 10,000 signing queries by calling some different implementations. So in other words, if one can query the same syndrome twice, they can mount a key recovery with non-negligible probability. Let's start from some background knowledge. Falcon was one of the 3 post-quantum signatures selected by NIST for standardization in 2022. So Falcon has a lot of advantages. It's the most compact signature scheme in the 3rd round of the NIST standardization process. So it has fast signing and verification. Falcon is a lattice-based hashed sign signature scheme. So we briefly introduced the hash and sign construction. In early constructions like GG and N2 sign, the public key is G and the secret key is B. So the secret B is a good basis which are respectively short and orthogonal, and the G is bad basis which consists of much larger vectors. So in his signing, he first hashed a message to a random vector T and then round the vector T to vector V, which belongs to lattice by using the good basis. And in its verification, it only checked if the vector V belongs to the lattice by using the bad basis G, and then checked if the vector V minus T is short. So the signing used deterministic algorithm to solve the approximate closed vectors problem. So the distribution of the signatures leaks the information of the secret basis B. So these early constructions, like GG and N2 sign, are insecure and then broken by Ren and Regif in 2026. So in GPW, the authors designed a provably secure hash and sign framework. They replaced the deterministic bar-byte algorithm with troubled sampler, and so in its signing used the lattice Gaussian sampling to prevent the secret leakage. So Falcon is efficient initiation of the GPW hash and sign framework over N2 lattices. So Falcon can be expressed the following formula. It is originally a GPU hash design framework and initiates with N2 lattices, which offers the compact list and combines some techniques like fast Fourier Gaussian sampling, which makes the sampling run increasing real time. So Falcon's main drawback is the overall complexity, which makes it hard to implement correctly, and the key generation and signing heavily rely on floating point arithmetics. In other words, for Falcon, is signing use the ring-efficient clean GPU sampler, and which involves a lot of the floating point arithmetics. For floating point arithmetic in Falcon, it's generally accepted that the double precision is sufficient. So in the state report on the third round of the list post-quantum cryptography standardization process, list raised a concern that the use of floating point arithmetic and the most complex implementations could lead to errors that might affect its security. In this work, we give the floating point errors sensitivity analysis of Falcon's Gaussian samplers. Next, we briefly introduce the Gaussian samplers in Falcon's signing procedure. In the left layer, FF sampler is the is a ring-efficient variant of clean GPU sampler, and the lattice Gaussian sampling can be reduced a series of integer Gaussian sampling with variable centers and standard deviations. And in the middle layer, sampler Z is the one-dimension integer Gaussian samplers. It first samples Y plus from the half Gaussian sampling by calling the subroutine base sampler, and then computes Y by using the random bit B. Then calculates X to perform the rejection sampling to obtain the target distribution. And finally, returns J by adding the integer part, the float of C. In our work, our work mainly focuses on the execution of sampler Z rather than its the distribution. So, say C and C prime are the two closed floating point arithmetics. For the standard deviation and the randomness, if the float of C is not equal to the float of C prime, so the two execution of sampler Z with respect to the center C and C prime has the same execution with the overwhelming probability. And if the float of C is not equal to the float of C prime, so the two executions are inconsistent. So for nearly integer center, sampler Z is sensitive to floating point errors. For FF sampler, we have the form of the centers Ci like this. So we have the probability of the first two centers respectively belongs to the center integers is equal to 1 over Q due to N2 simplicity, and the last two the probability of the last two centers respectively belongs to the integers is equal to the 1 over Q, 1 over the norm of the square of norm of the secret key, and the probability of the other centers belongs to the integers is approximately equal to 0. So for the first two centers or the last two centers, the probability belongs to the integers is between 1 over 10,000 and 1 over 20,000. So next we show how to exploit the floating point arithmetic discrepancies to perform the key recovery. For the syndrome view, by directly hash the message or by adding some fixed short. For Falcon's signing, inherently samples an integer vector Z and outputs a short signature S is equal to U minus J multiplies the secret basis B. So due to the floating point arithmetic errors, the signature difference for the same U is delta S is equal to delta J minus multiplies the secret basis. So when the floating point arithmetic instability only occurs in the last two costs of the sample Z, so we can eliminate the delta JE, J1 and the delta 0 is a short polynomial. We can use the simple exhaustive search to perform the key recovery. So our attack is not directly affect the planned Falcon signature, but it still has little impact on planned signature since due to the repeatless randomness. And our analysis directly relevant to the deterministic Falcon, which is specified by Laser and Chris packet. Such design has been considered has been applied to achieve more efficient, slightly friendly signature aggregation. And our attack has critical impact on Falcon-based identity-based encryption. Such constructions has been considered in Lattice identity-based encryption. Falcons in this construction, Falcons the key signature generation becomes the key instructions if the register users can query their key on given identities twice, so that the authority has the chance of leak the master key if the floating point arithmetic errors exist. So next we turn to the questions of how the floating point arithmetic discrepancy can arise. Floating point arithmetic does not obey associativity and or distributability, which linked weak determinism. We experimentally validate two possible sources for such floating point arithmetic discrepancy in Falcon. The first one is two almost but not quite equivalent signing modes, dynamic mode and tree mode. The dynamic mode is computes the Falcon tree on the fly, and the tree mode pre-computes the tree and store it as the inputs. And the second one is the different floating point instructions FMA. So for the two signing modes, the different computation order can lead to different evaluation of T1, which might affect the centers of sample Z. And in polynomial merge operation, so floating point arithmetic is again not distributive, so the combination of T may value different values in two signing modes, which affect the centers of sample Z. So we provide the experiment results within 10,000 for the two signing modes. Discrepancies within 10,000 signature pairs, one can mount for key recovery. And FMA and the other sources is FMA instruction, floating point instruction. So floating point, this kind of instructions are more accurate by just using one rounding only. So which also is the sources of floating point arithmetic discrepancies. In both signing and key generation, these instructions are widely used. So we also report the experimental results. Exact secret key can be also recovered within 10,000 signature pairs. So finally, we proposed some countermeasures to mitigate to make this sensitive to floating point arithmetic. we first provide the new sample Z with the stability of floating-point arithmetic errors. We replace the flow operation with rounding operation. So the sentence is changed to the half integers, and we further restrict the secret key, the square round of secret key to be ordered integer in key generation. So we also use the simple checks. We just, for the two signing modes discrepancies, we just reorder the computation order in three modes, or just avoid the reorder oaths to mitigate the discrepancies. And for the FMA discrepancies, we just disable it. So to avoid the floating-point arithmetic discrepancies, we just for the signs in the same settings, we just used the same signing modes and the same floating-point arithmetic implementation. So in conclusion, our attack is equal to the deterministic distributing Falcon with some floating-point arithmetic catalysis. And we also provide our artifacts in our public GitHub repository. Thank you for your attention.
Any questions? So I guess the computation is dependent on your programming and the FMA modes. So how is this countermeasures going to affect efficiency? Do you know?
You mean the discrepancy of the FMA instructions?
Well, so if you disable FM, disable
we
FM,
we just directly disable the instructions. In the codes they have the micro options to just disable it.
right, so it will presumably be a little slower.
Oh, might be fast. Yeah, because the FMA instruction based on the AVX2 instructions, right? So we just, if we just disable it, maybe it's slower than the original one.
Okay, I see. By how much?
We do not test it.
I see.
Test it.
Anyone else with a question? Well, I mean, then we can get to lunch.